All right. I'm going to be adding more sort of sample processing stuff to Blockhead, and so I've been revisiting the existing um, granular resynthesis algorithms that I have, because I'm going to put like a version of that into the new stuff. And so I've basically rewritten all of the sample analysis stage of that algorithm, because that algorithm needs, when you load in a sample into some process that uses that algorithm, um, it will kick off a background thread and like analyze the sample and then generate some analysis information. Um, and so that I've basically rewritten that, and now it's slightly better, slightly more costly, but uh, it's slightly better quality now, in my opinion. But basically, what I've been working on, I was going to talk about. Um, so there's this thing called DC bias or DC offset, which is where you have some kind of waveform. This is 0, 1, -1. So you have some kind of waveform like this. This is a nice waveform. But you could also have a waveform that looks more like this, for example, or maybe it starts down here and then it drifts away from the center. And from an audio production point of view, that's perfectly fine. That's basically a valid waveform, even though it's drifted off of the center line like that. But from an audio programming point of view, especially when it comes to like sample analysis stuff, and any like time domain stuff, that's kind of a nightmare. For me at least, because of the kind of sample analysis that I need to do. I'm basically relying on the fact that the sample is like crossing this 0 point at semi-regular intervals, because I'm like looking at the spaces between the 0 crossings for my analysis. So if I have a sample that's doing something like this, that's a nightmare for me. So what you can do, so this is called DC bias when it's not on the center like that. But you can cancel the DC bias, and if you go on the internet and look up how to like correct or cancel or like correct the DC bias. Sorry. Basically, all anyone has to say about correcting DC bias is to use a high pass filter, and it's sort of easy to understand why a high pass filter would work, because, for example, if you have a low sine wave that's like brrr, like that, and maybe you also have a high sine wave that's like beep. If you add those two together, then if you mix those two signals, then you'd end up with something that looks like that. I'm trying to draw it with a mouse, but you understand what I'm trying to draw, right? It's basically those two signals mixed together. So if you were to apply a low pass filter to this, then basically you're cancelling out this low frequency. If you apply a low pass filter to this signal, you're cancelling out this high frequency signal. So you're cancelling out this one, and what you end up with is something like that. But if you apply a high pass to this, then what you're cancelling out is this low frequency signal, and so you should end up back to something like that. So it's easy to imagine why a high pass would also work to correct DC bias, because say you have a sine wave like that, and say you zoom into a section like this, that would basically look like that, right? Which is like the same as like a DC bias signal. So that's why applying a high pass filter to this bit would basically bring this back down to the center. So the problem with using a high pass filter though to correct DC bias is filter introduces a little bit of delay, which is not it's not the end of the world, but if you're doing like sample analysis stuff, and part of the reason I'm revisiting this analysis now is to try to improve the quality a little bit and make it more accurate as best I can. I'd rather do it without introducing any delay. And so another way you could do it is essentially you could just split this signal into like windows. So you look at each window individually, and let's get a better example. So it's drifting off the center, and this is the part that I want to correct, right? So I'm just going to split the signal into windows of a certain size, and I'll get back to that in a second. And for each one of these windows, let me look at this one for example. I find the lowest value in that window and the highest value, and then I calculate the midpoint between those two values, and that value is basically how far off from the center we are. And so again we would detect the lowest point and the highest point, find the midpoint. Same again here. So we keep doing this for each window. So we end up with these values. These are the interesting values because this is like the distance from the center. So essentially what we want to do is adjust these so that those center points are actually on the center. But if we just do it like this, obviously this is going to introduce all kinds of artifacts because suddenly we've got these like jumps in the waveform, like there to there to there to there. Well, that would already also be moved down, but anyway. So instead of doing that, we basically we calculate a value for each frame in the entire sample by basically interpolating between these midpoints like this. So we'd end up with something like that. And then for each individual sample, we use this value we just subtract that value to get the signal back down to the center point. And so then an obvious question is, how big should these windows be when you're doing the analysis? And what did I decide on in the end? The sample rate of the sample divided by 20. Why did I decide on that? Oh, right. Okay. I tried a bunch of different things. Basically 20 hertz is the lower range of human hearing. So if I create these windows at intervals of like 20 hertz, then theoretically we're not interfering with the audible content of the signal. That's the theory anyway. Not that that would matter that much because this is only being used for analysis anyway. Like the user is not going to hear the result of this. All I'm doing is like I'm just removing the DC bias so that the signal can be analyzed further. Also, I did a bunch of like tuning with this and fiddling around with it and trying to figure out how it interacts with the second part of the analysis, which is what I'm going to talk about in a minute. But one problem I had was I would have a signal that it basically had like background noise at the start because it was like an acoustic sample. So there's a little bit of this sort of thing happening. And then there was something like this, and then the actual start of the drum or whatever it was. And the first window was something like this. And so I was detecting this as like the max and this is the min. So the midpoint is here. And so everything gets like, this entire section would get like shifted upwards. And so previously we had these parts of the signal which was like going up and down past the center point with these nice zero crossings, which is exactly the kind of thing that I want for the analysis. But now I've adjusted it so that that's not happening anymore. So I've actually removed zero crossings when the whole point of this is to get more zero crossings for the analysis. So what I ended up doing was the strength of the DC bias correction is greater the further from zero it is. So if I just detect these midpoints that are quite close to the center line anyway, then I only just adjust it by I think it's like power of 3 or something that I adjust it by. So so now these little moments like this get adjusted a lot less, whereas if the signal really drifts off from the center line, it will get more adjusted. The further it drifts, the stronger the correction. All right, so that's the work that I did on DC bias correction. It seems to be working okay. Possibly I can like tune it better with more sort of trial and error, but it would have to be trial and error because I don't have any like formal education in digital signal programming or anything like that. So I don't know. Like from an academic point of view, I have no idea like what the correct thing is to do. So it's all like trial and error, and just trying stuff out. So the reason that I need to do this, the reason that I like having these zero crossings is for the second part of the analysis, which is called this thing called autocorrelation, which is basically it's sometimes referred to as a kind of like pitch detection algorithm. It's not really. It kind of is. It's basically wave cycle detection, which is sort of related to pitch detection. It can be used for like rudimentary pitch detection, but anyway, let's say you have a signal, a nice simple sine wave that looks something like this, and every time the signal goes from negative to positive, that's called a zero crossing. So there's a zero crossing there. There'll be another one there. When it goes from positive to negative, you could also call that a zero crossing, but in my code, I don't call that a zero crossing. I only consider negative to positive to be a zero crossing. So that's what I'm looking out for. And this positive to negative, that is relevant. I'll talk about that in a second. I do use that for something, but so once I locate these zero crossings, I can basically separate the signal into these sections, and these are called wave cycles, or I think sometimes they're referred to as wavelets. I'm not sure if that's correct. Again, I don't know anything. I have no academic background in this stuff. Uh, right, no, sorry, I'm getting ahead of myself here. Let's go back. So forget the zero crossings for a second. So this thing called autocorrelation. The idea is it's a way of detecting repeating patterns in a signal. So let's say instead of having something simple like this, you actually have something that looks more like. Again, I'm drawing this with a mouse, so sorry if it's not. You understand what I'm trying to do with my mouse, which is, if you have a signal like this, as human beings we can look at this and we can see the pattern, but computing it in code is a bit more tricky, because essentially we can see that the repeating section basically looks, it's from this zero crossing to this zero crossing, but we've also got like these other zero crossings in the middle. So there's a zero crossing there, zero crossing. I'll just mark out these zero crossings. So the wave cycles that we want to detect is from here to here and then here to here. So each wave cycle has two zero crossings. The one at the beginning and then there's another one in the middle. So just looking at the zero crossings alone is not going to find us the wave cycles, because what we're going to end up with is this. Which is not what we want. So there's this thing called autocorrelation, which if you look it up online, the way people will describe it is what we're going to do is we're going to separate the signal into these windows, again, like we did with the DC bias thing. In fact, it's just two windows like this. And then we're going to go like at regular intervals or even frame by frame, we're going to compare this value with this value. And then we're going to compare this value with this value. And then compare this value with this value. And this value with this value. And continue all the way through the entire window. And then we're going to add up the differences between, so the difference between that and that and that and that and that and that. We're going to add up all the differences and get a final value. And then we're going to remember that value. And then we're going to increase the size of the window by a little bit, like this. And then we're going to do the same thing again. Compare this with this. Compare this with this. Compare this with this, all the way through, and then we get another value. We keep doing that, and eventually, if we do that for long enough, we might get like lucky, and we might end up with a window exactly like this. Looks something like that. And then we're going to compare this with this, and add up all the differences, and we get a really low value then, because it's almost exactly the same signal. We can see we get 0.000 or whatever, whereas the other ones we might have been getting values like 1 point something, I don't know, 3 points, whatever. And so we keep trying this with different window sizes, and then we find the one that ends up with the lowest diff value, and we go, that's our favorite one, that's the wave cycle that we've detected. Right, that is insane. That is such a stupid way of doing autocorrelation. It's kind of frustrating that if you look up autocorrelation online, that is the that is the way it's described. So a long time ago, this was like years and years ago, back when I was doing stuff with Reactor, I figured out a much better way of doing autocorrelation, in my opinion, or at least for certain use cases. This is just miles better. And what you do is you find all of the zero crossings, first of all. So here's our zero crossings. And we make a note of all of these These are our wave cycles that we're going to be working with. So make note of all these wave cycles. And so that's supposed to pass through the zero crossing. But anyway, so the first thing we do is we're gonna start. So for each one of these wave cycles, we're going to do an analysis, one by one. So this one, this one, this one, this one. We're going to do an analysis for each one of these each one of these individual wave cycles, and we're going to start at depth, like depth equals 1, and what that means is we're going to look at for this wave cycle, we're going to look at this one and the one right next to it. So depth 0, 1. And we're going to find the highest point, which is here. And that's called the zenith. And we're going to find the lowest point, which is here, which is called the nadir, I believe. And we're going to find the point at which the signal drops from positive back to negative. It will always happen at least once in each of these wave cycles by definition. So that's happening here, and what I call that in the code is the dive. And then I'm going to get a bunch of information about these points. So I want the value of this this zenith, and I want the distance from the left-hand edge, and I want the value of the nadir, and I want the distance again from the left-hand edge, and I want the distance of the dive from the left-hand edge, and I want the width of the wave cycle here. So I've got two pieces of information here, 2 here, 1 here, 1 here. So 2, 4, 5, 6 pieces of information that I'm going to compare with the adjacent wave cycle. So again, I'm going to find all of the same information. That's the zenith, nadir, with the value and the distance, and the dive, and the width. And I'm going to compare this with this, and compare this with this, compare this with this, compare this with this, and I've end up with some diff value. It might be like 1 point something, whatever. Because we can see, right, just by looking at it, that these are not very similar, because one's much smaller than the other. So that's depth 1, and then we go on to depth 2. So hold on, let's say depth 1 equals this value. So then we go on to depth 2, and depth 2 means 0, 1, 2. And so we're going to compare this wave cycle in the same way we compared this with this. We're going to compare this wave cycle with this one, and this one with this one. That's what depth 2 means. And then after we do that, then again, after we're going to, from that comparison, we're going to get another diff, which is going to be probably something, in this example, it's going to be something much lower. It'll be like whatever. And we will make a note of that as depth 2. So that one's winning so far. And then we go on to depth 3, which is we're going to compare this one with this one, and then this one with this one, and this one with this one. So the size of the total depth of the the comparison is 3 wave cycles. It's 1, 2, 3, 1, 2, 3. So we keep doing that up to, I can't remember what's my max depth at the moment. Oh, well, this is parameterized. So with Fudge sampler plugin, the depth is 64. So I do that up to 64, which is quite high. But that gives you a pretty good, like if you do have like a really complex waveform and it's crossing the 0 boundary, when it's crossing the 0 line many times, then it gives you a better chance of noticing these kinds of patterns, the higher the depth is. And so once we finish that, we just look at the depth that had the lowest result, and that's our favorite wave cycle. So in this case, it would probably be depth 2, which was this, and so that's our wave cycle. And so from that we can deduce, well, basically we have like this width is what we were looking for, and from that you can deduce if it's a relatively simple like tonal sample, then that would be a pretty good indication of the that would be a pretty good pitch detection. But that kind of wave cycle information, it's also useful for like more complex sample data as well.